continue our discussion with propagation of expansion wave through a fluid, of course, one dimensional expansion wave of finite amplitude. What we consider that if we create a pressure disturbance suddenly, particularly that is if we lower the pressure suddenly, then the fluid in contact with that lower pressure region will have acquired a velocity, and at the start or at the beginning there will be a step distribution of fluid particle velocity and also of pressure. The situation can quite easily be realized if we consider a cylinder piston system and the piston is withdrawn impulsively, let us say with the speed u p. So, at the start there will be a step distribution of velocity and pressure. However, this and a wave will be created, but since the expansion wave begins to flatten as soon as the wave starts propagating, this step distribution will not be remaining, and after some time the particle velocity will have a linear distribution and the pressure will have a corresponding distribution which is continuous. Now, as the wave starts travelling to the opposite direction to which the piston has moved, the front of the wave will move at the local acoustic speed, or that is the acoustic speed corresponding to the undisturbed pressure and density. Now, as distance increases, the expansion wave or the characteristics become wider because the expansion wave flattens, and this expansion waves will be limited by the terminating characteristics, which has the speed as we have derived earlier will be, that is speed of the terminating wave where, as you have mentioned earlier, that A4 is the speed of the wave front, or which is the acoustic speed corresponding to the undisturbed condition. So, between the terminating characteristics and the wave front, the speed of the wave continuously decreases, that is the wave front has the maximum speed of A4 and subsequent part of the wave travels at a slower speed with the terminating portion travelling by this speed. Now, these characteristics may tilt to the left or to the right depending upon whether this A4 is greater than or less than this. That is, characteristics tilt to the left or to the right to the right or left, which depends on whether A4 is greater than or less than gamma plus 1 by 2 u p. Behind the terminating characteristics, the flow properties are uniform, and for a perfect gas, these properties, that is flow properties behind the characteristics, terminating characteristics are if we denote them by say the behind and front as you have denoted by 4 is 1 minus of course, this relation comes directly from the relations that we have derived earlier for density ratio for a finite wave amplitude for perfect gas. Of course, this holds for perfect gas only. Similarly, the pressure ratio, that is pressure behind this terminating characteristics and ahead of the front, is similarly given by 1 minus gamma minus 1 by 2 u p by this should be A4. These are of course, the isentropic relations, because in this case the wave always remains isentropic, not like the compression wave which reaches a stationary state and changes to a shock wave. As you have discussed earlier, that isentropic waves becomes flatter and flatter, and expansion wave becomes flatter and flatter, and they always remain isentropic. So, essentially these are isentropic relations. This pressure ratio is usually treated as or called the expansion strength. So, this is called the strength of expansion wave. And from here we can see that the maximum theoretical maximum strength is when and this implies that the pressure behind the terminating characteristics and that is when it is a vacuum behind the terminating characteristics. So, that is the theoretical maximum possible expansion strength, and this implies that the all the internal energy of the fluid is converted to kinetic energy. That is, this implies internal energy of the fluid converted to kinetic energy. And if this u p is higher than that, that is in case of that withdrawing piston, if the piston speed is higher than that, then it will have no further effect on the flow. The wave that has been produced by this impulsive withdrawal of piston is called a centered expansion wave, because the characteristics looks like a fan. The expansion process is called, this is termed as centered expansion wave or expansion fan. So, we have seen how a finite compression wave and a finite expansion wave propagates in a fluid, and with this at our disposal, we can now go back to a shock wave, that shock tube problem, but the nonlinear case. So, we will now go to the shock tube problem with finite we have earlier discussed the shock tube problem, where the pressure ratio was marginally greater than 1, that is the pressure difference across the diaphragm was just infinitesimal. The shock tube, as you have earlier said, is a very simple device which contains a tube separated in two parts by a diaphragm, and the two end of the tube are connected to two chambers, where the gases are stored at higher pressure. In the earlier linearized case, we consider that the difference in the pressure between these two chambers is very small. So, that when the diaphragm is removed, the disturbance that is created is a very small disturbance, very small, and small amplitude waves are created, which could be analyzed using the linearized theory. However, what we will now consider is again that same shock tube, but connected by separated by diaphragm, where this is connected to high pressure and low pressure. This low pressure region will denote as region 1 and this high pressure region will denote as region 4. So, that pressure here is P 4 and here is P 1, and what we call that P 4 by P 1 is considerably larger than 1. So, this diaphragm is separating now two chamber, that high pressure and low pressures, which are also called the compression chamber and expansion chamber. This P 4 by P 1 is basically the characteristic parameter of a shock tube, because that is what we usually control. And in addition, we may also consider that the temperature at the two chambers are different. Even we may consider that the gases at the two chambers are different, having different properties. Let us in this case consider both the gases are perfect gas. So, gases in compression and expansion chamber may be different. Chambers may be different. However, we consider both to be perfect gas with say gas constant R 1 and R 4, that is both are perfect gas, but the properties here both are perfect gases. Now, let us say at the time t equal to 0, we burst the diaphragm, and at that instant then the diaphragm is burst at t equal to 0. And consequently, the pressure distribution at time t equal to 0 can be a step distribution at time t equal to 0. However, this step splits into a shock wave which propagates into the expansion chamber and an expansion which propagates into the compression chamber. The shock propagates to the expansion chamber with speed. This step splits moving towards the expansion chamber with speed u s and an expansion wave, an expansion wave moving toward compression chamber with speed a4 at the front. That is, coming back to this figure, when the diaphragm is burst, we have a discontinuity in pressure here P 1 and P 4, a jump in pressure, and consequently a shock wave moves toward. Of course, it may start as a finite wave compression wave, which essentially will convert into a shock wave very soon, and then this shock will propagate towards this expansion chamber with speed u s. Similarly, an expansion wave or central expansion will also be created here, which will move towards this high pressure region, where the front of that expansion wave will move with the local sound speed corresponding to the undisturbed condition in this high pressure chamber, that is A 4. Now, after a little time t 1, the shock has moved to certain distance within the low pressure chamber or the expansion chamber, and similarly the expansion has covered a certain distance in the high pressure or compression chamber, and what in essence happens that let us say this is the original diaphragm location, which we denote as x equal to 0, original diaphragm location. So, this is what is the original diaphragm location, and a shock wave has moved a certain distance and similarly the expansion wave has that is the condition of the fluid which is traversed by the shock, we are denoting by 2, and similarly the fluid which is traversed by the expansion wave, we are denoting by 3, and the interface between these two regions, these two regions we call contact surface. That is, this part of the fluid is traversed by the expansion wave, while this part of the fluid is traversed by the shock, and this interface between these two regions we call it contact surface. Essentially, it marks the boundary between the fluids which were initially on either side of the diaphragm. That is, this fluid was initially to the left of the diaphragm, similarly this fluid was initially to the right of the diaphragm, and since this part of the fluid is traversed by a shock wave, its entropy has increased, while this part of the fluid is traversed by an expansion wave which are essentially isentropic. So, the entropy of this part has not changed, it has remained what it was before the diaphragm was burst. Hence, there is a difference in entropy between the region 2 and region 3. So, even though there is no physical barrier between region 2 and region 3, the fluid in region 2 and fluid in region 3 have different properties, particularly their entropy are different, and usually these two fluids do not mix, they are permanently separated by these contact surface. And let us say in this situation, this is at time, say we will call it at t equal to some time t 1, in this part the pressure still remains P 1, in this shock there is a jump, the temperature distribution can be remember the pressure change here is not a jump, but a continuous process. In terms of characteristics or wave propagation over time, we can also depict it like this. This is x equal to 0, time t at time t equal to t1 . Expansion front, this is the shock, and let us say this might be the contact surface. Region 1, this is region 2, this is region 3, and this is region 4. Now, on either side of this contact surface, the temperature and density, they can be different. However, the pressure and flow velocity, they must be same. That is, on either side of the contact surface, denoting by the appropriate symbol 2 and 3, we have P 2 equal to P 3 and U 2 equal to U 3, but entropy, as we have already seen, that or rather eventually entropy at region 2 is higher than region 3. Now, the contact surface velocity must be u 2 equal to u 3 . Now, if we can find this ratio of pressure between region 1 and region 2, that is P 1 by P 2, and similarly the ratio of pressure between region 3 and 4, P 3 and P 4, using the shock wave and expansion wave relationship, and which we in turn we can express in the form of velocity, that is the velocity two speeds u 2 and u 3 can be from shock relation, that is Rankine-Hugoniot which we have derived earlier for the moving shock problem. Similarly, considering the expansion part, we can write this velocity to a 4 by it should be noted that we are considered the possibility of two different gases in the expansion and compression chamber, which are denoted by gamma 4 and gamma 1, as we have earlier mentioned of R 1 and R 4. That is the specific heat ratio of the gas in the high pressure chamber is gamma 4, while that at the low pressure chamber is gamma 1. Now, since u 2 and u 3 are same, we can equate the right hand side of these two relations, and consequently what we get is P 4 by P 1 equal to P 2 by P 1 1 minus that is the shock strength P 2 by P 1 we have got as an implicit function of the diaphragm pressure ratio as you mentioned earlier. This diaphragm pressure ratio P 4 by P 1 is the most basic parameter and which is in control of the experimenter which is in control of the user, and hence it is the basic input for this problem, and this P 2 by P 1 we can evaluate implicitly, which is now an implicit function of P 4 by P 1. So, P 2 by P 1 is the shock strength, and this P 4 by P 1 it is called diaphragm pressure ratio. The expansion strength P 3 by P 4 this can be obtained as P 3 by P 4 equal to that is the shock strength by diaphragm pressure ratio is the expansion strength. Shock strength by diaphragm pressure ratio gives us the expansion strength. The temperature and density, as you mentioned, that in region 2 and region 3 are usually different, though the pressure and velocity across the shock and expansion are identical, but the pressure, density and temperature they are usually different, and the temperature behind the expansion we can obtain using the isentropic relation, which is say T 3 by T 4 can be obtained straight away by P 3 by P 4 to the gamma 4 minus 1 by gamma 4, which again is shock strength by diaphragm pressure ratio, which we have already seen P 2 by P 1 by P 4 by P 1 . Similarly, the density ratio, similarly rho 3 by the temperature behind the shock T 2 from Rankine-Higoniot relation rho 2 and T 2 similarly can be found using the Rankine-Higoniot relationship, and that is T 2 by and now this shock tube can be used for a short duration wind tunnel also and for various studies in shock. However, the duration of the flow in this case is limited by the length of the expansion and compression chamber. Since both these expansion waves and the shock wave, they will reflect from the end of the chambers and they will eventually interact with each other. So, after a long time, this simple configuration will not exist within the tube and since in this case the flow speed can be very large or the flow speeds are very large, the duration is usually very small in terms of few microseconds. Now, this simple relation or one dimensional analysis holds quite good as long as the pressure ratio remains moderate. However, for a very large pressure ratio, the effect of the starting waves, the 3 dimensionality and the dissipative effect of viscosity and heat transfer, they come into picture and the relations or the analysis deviates considerably from the real situation. However, as long as the pressure ratio, that is the diaphragm pressure ratio remain moderate, the relations are quite useful and quite accurate. So, what now we can see that if a body moves through a fluid, it creates a disturbance and these disturbances are propagated in an elastic media as a compression and expansion wave. We have seen that as long as the disturbances are very small, that is the waves are of very small amplitude, they behave linearly, their shape remains almost undisturbed, the shape is permanent, the wave speed is continuous, wave speed is constant, which is the local acoustic speed. However, when the wave is finite, the nonlinearity comes into picture and because of this nonlinearity, the different parts of wave travels at a different speed and from our analysis we have seen that for all real fluids, the expansion part flattens and the compression part steepens. As the compression part steepens, the gradients in velocity and temperature, they become high, they can no longer be neglected and consequently, the dissipative action of viscosity and heat transfer or conduction comes into effect and sooner a balance between this dissipative mechanism and the nonlinear steepening effect come into balance and the compression part of the wave reaches a stationary state without any further distortion and becomes a shock wave. However, the expansion part of the wave flattens because of nonlinearity and consequently, the gradients become smaller and smaller. So, that the dissipative actions or diffusive actions can never become considerable and the wave remains isentropic throughout and no stationarity can occur in expansion part of the wave, that is that no expansion shock can occur. Shock can occur only in the compression wave. With this, we have finally analyzed the shock tube relation, shock tube for finite pressure ratio, where we have seen that as the diaphragm is removed, a shock travels to the expansion chamber and the expansion travels to the compression chamber, and the fluid which are behind the which are on the two sides of the diaphragm, they do not mix. They have there is the contact surface is permanent. Of course, where we are considering that the waves are not reflecting back and interacting. So, this contact surface is permanent, and beside the two sides in the contact surface, the pressure and velocity are same. However, temperature, density and entropy, they remain different. And also we have mentioned that these one dimensional relations obtained from a very simple analysis are quite accurate as long as the diaphragm pressure ratio remains moderate. With this, we will conclude our one dimensional flow for the time being, and we have seen that in one dimensional the flow, the compression part becomes a shock wave, and since in this case the only compatible shock wave is normal shock, see in one dimensional flow only normal shock, one dimensional implicit flow only normal shock can occur. Expansion we have seen that can never reach a stationary or never reach a shock like condition. Expansion part of the wave or expansion always remain isentropic.